Everything good? Yeah, all right. See, we're getting better at this. Yeah. Better? Okay, so I guess we should probably start. My last class, I had to, I'm not sure if you guys have to do this. You probably do, but maybe you do, I don't know. But last class, I had to sort of arrange midterm week. So I have to bring in like half the class at a time. I did 2 tests. Yeah. So just, the scheduling and everything has to be sort of done appropriately. So I'm glad we don't have any tests in here. So that's the situation. All right, so today what we're going to do is we're going to talk about finite dimensional algebras, and we're going to talk about the theory of idempotence. And this goes back to many, many years. The first place I sort of learned about this is in a book by Curtis and Reiner. So let me just write this down. So A here is a finite dimensional algebra. And let's say it's over field K. Okay, so it's a ring which is a vector space over K. And we're going to talk about idempotence. In A. And so this theory can be sort of found in a book by Curtis and Reiner written back in, I think, 1962. Did you ever meet Charlie Curtis when you were at Oregon?
Oh, no, I think so.
Yeah, so he's kind of legendary there. I think he must be close to, oh, he's definitely over 90.
Yeah.
Yeah. So anyway, so Curtis was a member of the University of Oregon faculty for a very, very long time. And Reiner was at Illinois, and they wrote this beautiful book. It was on associative algebra in 1962. So if you're interested in seeing like all the details of this, I would refer you to this book. But there's a lot of theory that goes on, a lot of proofs, but we're not going to be able to go over all the proofs. So I just need to highlight some of the important properties. All right, so what's an idempotent? So an idempotent is an element inside of A such that what E squared is E. So for example, the identity is an idempotent, trivial idempotent. So there's something called I can never get this right, whether there's I before E or E before I. So let me see what I have here. I have spelled Pierce wrong. So a lot of times we call this a Pierce decomposition. So let's say E is an A, E is an idempotent. And what we can do is we can sort of split A up. So we have that 1 over 1 minus E is an idempotent. And it's orthogonal in the sense that when I take the product of the two idempotents, I get 0. Okay? So E times 1 minus E equals 0, because that's pretty obvious. Okay? So E and 1 minus E are orthogonal. And whenever you have orthogonal idempotents like this, whose sum is actually equal to 1, then I can split A up. So A is A times E, and I can make a direct sum decomposition with 1 minus E. Okay? Now, when you look at this decomposition, what do we know? Well, we know that A is a free module. These two are A summands of a free module. So therefore, EA and A times E and A times 1 minus E are projective modules. So idempotents allow you to split the algebra into projective modules. Now, what I can do is I can go further, and this takes some proof, but you can do the following. So if you take sort of a more general version of this, what you can do is you can sort of take 1 and split it into primitive idempotents, which are orthogonal, E1, E2, up to EM. So you kind of repeat this process, and the PIs are primitive idempotents. Okay. So what does primitive mean? It means that EI is not equal to, let's say, F1 direct sum plus F2, where none of these idempotents are equal to EI. Okay. So this cannot happen. So you can't split the idempotents up any further. And what I want to impose is that, again, that these idempotents are orthogonal. And then once I do that, I can split the algebra up in terms of projective indecomposable modules. And A times EI, I'm going to call it projective. You can't split them up anymore, and so the projective indecomposable modules. So the projective indecomposable modules can be obtained by just taking this sort of idempotent decomposition and sort of looking at the factors. Okay.
So why do we know that primitive idempotents exist?
What you can do is you can just iterate this process kind of over and over again, and it's going to have to stop. Now, you may know about this theorem, like if you take a semi-simple like algebra, then it's a isomorphic to direct sum of matrix rings. Right? So this algebra here may not be semi-simple, but when you take the algebra modulo its radical, it turns out to be semi-simple. And so this will be related to this idempotent decomposition too. It's compatible with the idempotent. All right. Okay, so next. So this is in terms of looking at idempotents in general, but now I want to look at special types of idempotents, which are called central idempotents. So now I'm going to do the same thing, except what I'm going to do is I'm going to look at CIs, which are I'm going to call central. So they're in the center of the algebra, primitive idempotents. Okay, and then I want them to be orthogonal down. So Ci times Cj is 0 when I is not j. Now I can do the same thing. I can split A up in terms of this decomposition, but when you look at A times Ci, it's not just a left ideal; it's a two-sided ideal too. Okay. So split up A in terms of AC1, direct sum ACM. A times Cj this is a two-sided. So the idea is that when you split something up in terms of central primitive idempotents, you get a decomposition of A in terms of indecomposable two-sided ideas. So this is a decomposition of A into indecomposable two-sided ideas. And these are precisely called the blocks. This decomposition is unique. There's sort of a quotient theorem for that. So the A times Cj, let me call this strip Bj, are called blocks of A. Okay, so people who have seen this before, if you talk to any like finite group theorists, like who works in modular finite group theory, probably has talked about blocks before in their talk. And this is precisely what they're talking about. Now, as I mentioned before, the blocks sort of make the algebra a little bit easier to study. So let me kind of say something about this. Okay. And maybe I should say this way. So here's a fact. So let M be an decomposable A model. All right, so there's a Kroll-Schmidt theorem, namely, like if you take a module, then it can always be broken up in terms of indecomposable modules. So I don't know, maybe I should state that too. Okay, so, well, let me just state this first. Okay. So let's say I have an indecomposable A module. Then it turns out that if you take any of the central idempotents and you apply it to M, then only one of them is going to be non-zero. So then Cj of M is not equal to 0 for only one. All right, so since, and the rest of them are equal to 0. And so the nice thing is now I can actually stick or say that this module belongs to the block Bj. So you say that the module belongs to the block Bj. Okay, so for any indecomposable module, it's only going to belong to one block. And so if I take any indecomposable, so let's say let N be an A module. Let's say it's finite dimensional. And it turns out that N is a direct sum of indecomposable modules. So N is going to be N1 direct sum N2 N where the NJs are indecomposable. And then what you can do is you can sort of put, you could actually look at each of the components and then look at the blocks that they belong to. Okay, so the way you can kind of think about the blocks are they're sort of like little receptacles for your algebra. So for any indecomposable module, you just look at what block it belongs to and you sort of throw it in that receptacle. And why is this useful? So this is useful. Because of the following fact is that x10 of A, let's say MN, is not equal to 0. M and N are indecomposable modules. So if the extensions, if there's any cohomology between the two modules, then they have to be in the same block. And they can't be in two different blocks and have cohomology in between. So let's say for some. Okay, so this is kind of a crash course in finite dimensional algebra theory and idempotency. Are there any questions on this? Maybe you've seen parts of this or some of this before.
Is there a way to, because I know idempotents show up as projections, right?
Yes.
So is there a way to sort of visualize these as projections in some kind of?
Yeah, exactly, because the p squared is e. That's projection. Right. See, if you like hit a module times e, right, and then you hit it again times e, then you stay where you are.
So we should think of like the image of everything of the form e times something is like the projection onto something.
Yes, that's right. Exactly. And that's what a projection is, or the projection operator is, right? You take p squared is equal to p. That's a projection operator. So. Very good. All right. Now, there's a different side of the story. So I want to actually talk about that. So I talked about idempotents. Now I need to talk a little bit about representations and how they relate to the idempotents. Okay. So let me erase this part. So I did it a little bit over here with the blocks, but what I want to do is I want to be more specific in terms of the simple modules and the projected modules. Okay. And then I'm going to do an example. So a definition, you've seen this before. So P is projective as an A module, if and only if P is a direct sum out of a free module. Okay. Now, if I take my algebra A, so A has finitely many simple modules, because it's a finite dimensional algebra. And let's label them by L1, L2, up to LT. Okay, so another way to say it is these are the irreducible representations for the algebra A. Now, for every simple module, there's a projective module which sits on top. So Li sits on top. So for any Lj, there exists a projective, indecomposable module. Well, this is the connection with the idempotents. call it Pj, such that Pj surjects on Lj. If I take Pj modulo its radical, then I get Lj. So I can just take the radical of the algebra times the modulo, that's the radical of Pj. Or I can think of it just like I've done it before. I can look at the smallest submodule such that the quotient is semi-simple. Okay? And then moreover, there exists an idempotent Ej, where Ej is a primitive idempotent. Such that I can realize this Pj as A times Ej. I can actually realize this projective cover as a summand of it. Okay, so this is kind of a nice story. You can actually get your hands on the projective indecomposable models in some sense, although it's a big question in representation theory, like what the structure of the projectives are in general. Okay, and a lot of times, so these PJs in the literature are called, so I just want to kind of the projective covers. In your representation theory course, did you do like Cartan-Brauer triangle at all? You talk about that?
Don't think so.
Okay. All right. Okay, so yeah, it's, if you do finite group representations, there's a beautiful theory involving these projective covers, looking at characteristic zero lifts of various finite group representations. Okay, so these are called the projective covers. And another term you might see for the projective indecomposable modules. And sometimes people in the literature, especially people in Britain, call them the pins. All right. Okay, now for every simple module, there's a projective cover. And there's a beautiful formula which generalizes the Wedderburn decomposition. So this is we call it a nice formula. And it basically says, if I take the dimension of A, I can take the sum of the dimensions of the projective covers and the simple modules, sort of take the inner product and then, of course, sum them all. So the sum of J equals 1 to T, the dimension of the projective cover for Lj times the dimension of Lj. Okay, so there's a really nice sort of formula which relates the dimension of the projective indecomposable modules, the dimensions of the simple modules, and the dimension of the algebra itself. And if you notice, if an A is a semi-simple algebra, the projective cover is actually equal to the simple module. Okay. So let me add A is a semi-simple algebra. And everything is completely reducible. So that means that the projectives are equal to the irreducibles. And when you write this out, the dimension of A is equal to the sum. Now, you've probably seen this in finite group representations over characteristic 0, right? So then you get dimension of LJ. So this is like the Wedderburn decomposition, right? Because you have a direct sum of matrix algebras, and those each have the square of the dimensions of the irreducible representation. Okay, so this is a generalization of sort of the Wedderburn decomposition that we have seen before. Okay, questions on this?
So I'm wondering for the LJs, is this the first step of a projective revolution?
Yes, it is.
So like if something go wrong, you can try to extend.
So you're exactly right. You take LJ, all right, and you can cover it with projection. Yep. And then you look at the radical, and then you cover that, right? So the radical you get, and you want to put another projective module here. So it turns out once you cover this or find the projective cover for this module, so there's sort of a whole theory of projective covers. So you just have to know what the radical of this module is. And you cover that with all the projectives. And then you use the projectivity problem to lift it to this map over here. And then you just continue the process. And that's how you construct a projective resolution.
So can I ask a question?
Yeah, go ahead.
So I know that there's some theorem that says that projective modules are equivalent to vector bundles in terms of
Yes.
like over schemes.
In terms of,
Over schemes. So like a projective model is equivalent to a vector bundle.
yeah.
So do you know, is there a way to visualize that here in this context?
Probably. Yeah, I'd have to look at it a little bit more. I can't think of it right offhand. So. I'm sure there is, though. Absolutely. Okay. Now, what I'd like to do is show you that it's not so easy finding idempotents. So I want to do like the easiest possible example of trying to find idempotents. And what I want to do is I want to point out the differences between varying the characteristic of the field. Well, maybe you've done this in group representations, but let me do it anyway. You can think of this as like Moshka's theorem for this very special algebra. Okay, so let's do an example. So I'm going to try to look at the most basic example possible. And this is the group algebra over the group Z mod 2. So it's only a two-dimensional vector space. So this consists basically of formal sums. Let me just write it this way. So if you take A1 times 1 and A2 times G. So Z2 has just two elements. So I take the identity element of the generator G, where G squared is 1. Okay. Is everybody okay with that? All right. Now, let's say I have an idempotent. So let's say E is an idempotent A1 times 1 plus A2 times G. Now, let's say I take an idempotent, so I have to take E squared, which is A1 times 1 plus A2 times G times A1 times 1 plus A2 times G. And, you work it out. And if I haven't made any mistakes, I get A1 squared, A2 squared times 1 plus 2 A1, A2 times G. Okay, let me use the 12. All right, so I'm assuming that it's an idempotent, so E squared is E. So that means that this has to be equal to A times 1 plus A2 times G. All right, now if A2 is 0, so let's analyze these equations. So we're just going to down and do this. So I have to have that A1 is equal to A1 squared plus A2 squared. Okay? And I have to have that 2 A1, A2 is equal to A2. All right, so first of all, if A2 is 0, so if A2 is 0, then, well, it's clear what happens. E is equal to A1 times 1, right? And we have that A1 is either going to be equal to 0 or 1, is that right? Yeah, so A1 is going to be 0 or 1. So then E will either be 0 or 1. Okay, so not much is happening there. Okay, you just get the obvious idempotent. Okay. So I'll call these the trivial idempotent. All right, so we sort of know there are trivial idempotent around. They're not very exciting. Now, if A2 is not 0, then we can divide. So if A2 is not equal to 0, then this equation here gives you that 2A1 is actually equal to 1. Okay. All right, so now what do you have to worry about? We'll conclude something about A1.
It's equal to half.
You're in Z2.
Well, I mean, so let me ask you this. I mean, when can I conclude A1 is equal to 1/2?
Characteristic of K is not 2.
That's right. So if the characteristic of K is not 2, okay, so this is an important thing. Then I have A1 is equal to 1/2. Okay? Good. Now, so if A1 is equal to 1/2, then I can actually put things back in up here. So what do I get? I get 1/2. So 1/2 is equal to 1/4 plus A2 squared. Right? Okay, so 1/2 is equal to A2 squared. 1/4. Okay. All right, so now I have two solutions. All right. So A2 is equal to 1/2, or A2 is equal to minus 1/2. So I get two idempotents, and those are going to be primitive idempotents. So then I get that E1 is equal to 1/2 1 plus g, and E2 is equal to 1/2 1 minus g. Okay, and I split things up very nicely with my algebra as long as the characteristic is not 2. So if the characteristic of K is not 2, i.e. doesn't divide the order of the group, then my algebra gets split up into A times E1 where it's some A times E2. Okay? And these are both one-dimensional. All right, so these should be matrix rings. And can anyone tell me what irreducibles they correspond to? What irreducible representations do you know for Z2?
Building the sign.
Like the trivial on the sign, right? Because Z2 is the same as sigma 2, right? So I have the trivial on the sign. You want to see right offhand which one is a trivial? Anyway, one is a trivial on the sign. I'll just say you guys can figure it out. Okay. The algebra splits up as a trivial plus the sign representation. Now, what happens if the characteristic is equal to 2? If characteristic of K equals to, okay, so let me just back up over here. All right, let's back up to these equations, right? So this is 0. Yeah. So that means that A2 has to be 0. But we already analyzed the case when A2 is 0. And the idempotent is either 0 or 1. So what that means is that the algebra itself is indecomposable. So this implies that A here is an indecomposable in fact, it's a projected indecomposable A module. A is projected. Okay. Well, it's a projective indecomposable A module of dimension what? Well, it's a dimension of A. Vector space. Well, what's the dimension? 2, right? Now, it turns out that, and this isn't taking much work, but it turns out there's only one irreducible representation when the field is characteristic 2, just the trivial representation. Okay. So the only irreducible representation here is just the trivial representation. Okay, so when the characteristic A is 2, and I'll call it L equals K, is the only irreducible rep, or only simple model. Okay. Well, that doesn't leave very much. So if I have this module over here, and the only irreducible representation is the trivial module, I have a 2-dimensional representation. then what does its composition series have to look like? It's only two-dimensional, right? How many composition factors?
One.
One? How many? The trivial module is only one dimensional, right?
Three, the whole thing, quotient, and the trivial.
Well, I mean, okay, so I take A, right? And I know I have, the only composition factor is the trivial module, right? So I have the trivial module sitting inside of there. Yeah? When I take the quotient, how big is it? Right. So I only have two composition factors, right? So A has A sitting down at the bottom. So this is in the socle. Okay. So that's in the socle. And then this is in the next layer out in the socle. Similarly, this is actually in the head, and it's A over the radical. This is the decomposition. And this is not, clearly not semi-simple. All right, so this is a very simple example in many ways. But what it does is it gives you the flavor of modular representation theory. Because unlike the case when we have characteristic zero, where you have the complete reducibility, like with Moschke's theorem, in the case when you have a characteristic where characteristic divides into the group, you may not have a semi-simple situation. Modules are not necessarily completely reducible anymore. And here's a classic example. So let me say this is modular vector. If you take anything away from today, you can just sort of think about modular representation theory as like even just taking projective indecomposable modules and finding out what the structure of projective indecomposable modules are. So we don't know the answer like to many, many situations. If you take the general linear group, for example, then you take a prime which divides the order of the finite general linear group, you don't know the answer to that question. Clearly wide open. Okay, any questions on this? So maybe I should mention one more thing about this. So one thing I hope is that, some of these principles you'll actually see in talks on representations. So let me talk about one more concept. And these are called Cartan invariants. Okay. So it's not hard to sort of state this. So right now, I gave you an example of a projective module. So this is the projective cover for K, right? And so you can sort of ask yourself the following. So if you take an irreducible representation for a finite dimensional algebra, and you look at its projective cover. So let's say that the L1 up to LT are the simple A modules. So you just break down all the possible simple A modules up to which are non-isomorphic. And then you take P1 up to PT. You take the projective covers. And so what you like to do is you like to know what the composition factors are inside of each of these projective covers. And that's what the Cartan matrix is. So when I write PI LJ, the number of times LJ appears as a composition factor of PI. Okay, so that makes sense, right? This the PI is just a module for this composition series. And what is the Cartan matrix? Cartan matrix is PI LJ. Okay, so the ijth entry is just the number of times LJ appears in something. And this is what's called the Cartan matrix. Different Cartan matrix than LJ, okay? This is a Cartan matrix in the theory of finite dimensional algebras. So it's not like with root systems or anything like that. This is completely different. It's still called the Cartan matrix. All right, so over here, right? So the Cartan matrix just involves one entry, you know, and it's the number of times the trivial module appears in here. So one entry is stupid. All right, any questions on this? Okay, good. So we have a little bit of time to start the new topic. All right, so maybe people might know more about this than I do, so I'm happy if you chime in. Let's see. All right. So what I want to talk about next are what I call group schemes. So I don't know what the best way to motivate this is, but a lot of times, you know, what you want to do is you want to sort of talk about finite dimensional Hopf algebras. So here's one thing is that when I'll mention this later on. So if you talk about group schemes, this turns out to be equivalent to finite dimensional co-commutative Hopf algebras. Now,
True for affine group schemes, or?
yeah, I should mention affine group schemes. So I was going to say this too. Okay, let me just put it affine. Okay, good. So now, the reason we like to talk about group schemes is they behave sort of similarly to groups. I could talk about sort of normal subgroup schemes, and I can take quotients and I do things in the appropriate way. And so the language is just, it's cumbersome working with algebras. It's much easier sort of working with groups in some sense. So this is actually a more, so I'd say this here is a more likable. More likable language. Everyone likes groups. Now, the disadvantage is it's more abstract. And And, you know, this is, I'm not exactly sure about the history about this, but I think it goes back to the work of Grothendieck, for example. And the thing is, it's more abstract, but in the same way, it's easier to work with in some sense. So what we'll do is we'll translate back and forth once in a while, but sometimes it's actually better to work with this side rather than this. So let me give you an example. Now I haven't defined anything yet, but this is just an example. So let's say G is a reductive algebraic group, and then I can word scheme here. Okay, so you could actually think of like GLN, SLN as a group scheme. Now you have a nice map, which is called the Frobenius map, which goes from G to G. Now there's a way to define it for any reflective group, but let me just do it for the general linear group. So if I take GLN, GLN, now the reason why I'm not putting like GLNC or GLN K, for example, inside of here is because you sort of insert the coefficients. You let the coefficients run over all commutative K algebras. And the Frobenius takes a matrix here, and it just raises each entry to the group column. Okay, so this turns out to be a map of group schemes, and
Is that a prefix something?
yeah, so whenever you have Frobenius, the field that you're working with has characteristics to be greater than 0. You know, you need it to be actually a map of groups. Okay, so when you do that, you can take the kernel, which I'm going to call G1, and this is also an affine group scheme. Okay, so it's not a group, it's not an algebraic group per se, the group scheme, but we still have a coordinate algebra. So we still have sort of functions which sort of define this group scheme. So this is a coordinate algebra. This is a good example to keep in mind. Okay, this is a finite dimensional algebra too. So this turns out to be finite dimensional. And then what I can do is I can take its dual. So when I take its dual, and let's call this A, this is a finite dimensional co-commutative off algebra. And the theorem says that representations for G1 are equivalent to representations for representations for G1 are equivalent to representations. And now you know why, now you can see why I wanted to talk about finite dimensional algebras, because sometimes you want to look at this in terms of group schemes. Sometimes you want to look at this in terms of finite dimensional algebras. So we want to kind of pass back and forth between the two languages. Okay. All right, so that gives you a brief introduction. So let me just kind of give you a flavor for what I mean by group functor. So let's see. Okay. So when I was first learning this, it was kind of hard to get my head wrapped around this idea. Here's kind of the way I thought about this. All right, so R is going to be a commutative K algebra. And I'm going to assume that I'm always going to assume that this thing has an identity inside. All right. So the idea is when you take the general linear group GLN, we sort of know what that means. Right? You just take matrices, which have some sort of like the determinant is non-zero condition. Right? So you usually plug in a field to GLN. But what I want to do is I want to think about plugging in any commutative K algebra into this. When I plug in any commutative K algebra, I spit out a group. So this actually gives you a functor from commutative K algebras to groups. Okay, so I can do GLN, I can do SLN. Right? So you just plug in any R into here, I get a group. So I want to consider certain functor, it's called K, it starts with F, and it's going to go from commutative K algebras and set me into it. Okay, sort of just by plugging in coefficients, that's the easiest way to see that. So in this case, you take F of, let's say, R, and then you get like GL and a Y. And this is actually a functor. So I want to consider this as a functor. And so therefore, if I have a map between commutative K algebras, I would better get a map between groups. So given map of commutative K algebras, and to get a map of covariant map, which goes S. Now, there's a way to sort of see the connection between affine group schemes. These are what are called affine group schemes, and also top algebras.
The targeting of this functor, something like you have more structure, ring structure or something. For K algebras.
You might, but right now you're just going for arbitrary K algebras. So you kind of have to set it up right to get this equivalence in some sense. All right. Okay, let's see. Oh. Okay. Are people familiar with representable functors at all? Yes or no? Kind of? All right. All right, so maybe I'll see. When are we supposed to stop here? 8 minutes. Okay, I think I'm supposed to stop, right? Okay. So we'll stop now, but next time what I'll do is I'll start in on some things about representable functors, and then I'll make the connection with algebras. I don't want to, spend like, you get to them in the first semester on this. I want to kind of give you a proceed on.
You do quantum stuff, right? Do you know what about crystals?